All right, how's it going, everybody? Happy Tuesday. We are here looking at our first day of the week right here since I got a little hung up with some of my stuff yesterday. But I am hopefully all good to go now. My morning things went fine here, so I think we can hopefully be all good to go today. Today we are looking at uh, our section 6.3, our method of cylindrical shells. And what's really important when we're talking 6.3 stuff is that we recognize that 6.3, that 6.1, 6.2, and 6.3 are all doing the same job for us. They're just handling it in different contexts. And this is one of those really important things where a lot of the things in this class are going to be just because you can do an individual technique does not necessarily get you there. A lot of this stuff is about strategizing and identifying when is one circumstance going to be better than another. Um, and verifying that different techniques are equivalent to each other is also a thing that we kind of care about here. What I kind of want to start with here is talking about like what have we been doing here so far in chapter six. In chapter six, we've basically just been figuring out how to find the volume of an object the whole time, and this is our third different technique here. I promise 6.4 and 6.5 will be different. 6.4 is exciting and different. 6.5 is going to be super easy with our average value stuff out there. So method of cylindrical shells. So again, make sure that you're thinking about this as a partner section with 6.1 and 6.2. This is the book just giving you three alternate techniques to compute volume, and depending on the circumstance, it might be better to use one method versus some other method. The important thing to me is that I always like to think about these things being in terms of our Riemann objects that we accumulate here. And so what we want to recognize is what is the Riemann object that is being accumulated in each of these cases. In section 6.1, we looked at cross-sectional areas of objects and we said, listen, if you can find a formula for the area of the cross-section of a solid object, then we can just take a bunch of sheets and add those sheets up and get a solid object, right? And I mean, that's basically just like what a textbook is, right? We take a bunch of one-dimensional objects, but when we add together enough two-dimensional objects, but we add enough two-dimensional sheets, we get a three-dimensional volume. So in section 6.1, we said it'd be cool if we could just take a slice, a cross-section of everything, and add up an infinite number of sheets to get a solid object. In 6.2, we said, well, there's other ways to do this. Sometimes finding cross-sectional areas is either difficult or impossible, so it's not necessarily something we can always do. In 6.2, we said, listen, if the solid object that you're trying to find the volume of could be described, if we could describe that volume as a 2D shape that's been rotated around some axis, then we can accumulate disks or washers as our pieces of cross section, and that will help us arrive at a volume. So in 6.2, our Riemann object was a disk or a washer that was infinitely thin or had like the thickness of like a dx or a dy. In 6.1, our Riemann object was a sheet that was attempting to match the shape of the object, right? In 6.2, we didn't say like, oh, that shape looks like this. Therefore, this is my Riemann object. It was always disks and washers in 6.2. In 6.1, it was like a custom object. It was like, based on the shape, can you come up with a cross section? So in 6.1, I think is sort of almost like the most custom way of doing this. 6.2 and 6.3 are more general ways of doing this that work for any shapes. In 6.3 now, we're going to say, sometimes the disk and washer method goes really poorly. Sometimes you end up reaching a point where even if you could do the calculus, you can't actually do the algebra. One of the things that we've seen is that we do a lot of bouncing back and forth between solving for x and solving for y when we talk about our stuff in 6.2, when we do our disk and washer method. And sometimes that results in things getting tough for us. Finding intersections of locations and all this stuff out there got a little tough, right? So what we're going to see in 6.3 is that some of the places where we would have reached algebraic roadblocks, those are not going to be such a big deal for us in this case. We shouldn't have to be doing a lot of this switching back and forth between solving for x and solving for y if we're appropriately using the cylindrical shell method. So instead, we're going to say maybe it's going to be better to accumulate cylindrical shells, an infinite number of infinitely thin hollow cylinders, and that's what's going to arrive at our volume. So what you should be picturing is sort of like straws that are all getting layered together. And if you had an infinite number of straws that had smaller and smaller and smaller diameters starting from an outer one, That would really just make one solid object. You would just end up with the entire cylinder right there. So what we're going to do is we're going to, rather than finding cross sections, rather than finding a revolution, okay, we're still going to deal with revolutions here, but rather than finding a disc or a washer, we're going to think about finding an entire cylinder, and we're going to add up a bunch of those guys. So I think our conceptual thing to see about 6.3, or rather, I should say, the conceptual thing to see about 6.1, 6.2, and 6.3 is our goal is the exact same in all three sections. Find the volume of a solid object. Our strategy is kind of the same. I mean, it's all still integration. The only thing that's really changing across each of these three sections is what is your Riemann object that you're going to accumulate an infinite number of. That's the only thing that we're really changing here. So all we're doing today is just using a different Riemann object, a cylindrical shell. I'm kind of hoping that this section is not the super. I think that 6.4 is the harder section of the week here. I think that tomorrow is going to be a little bit tougher, that I'll have some more stuff to talk about. So I'm not planning on today being excessively long. I'm planning on tomorrow being excessively. I never plan on that, but you guys have already seen that's sort of what happens there. So I'm kind of hoping to keep today relatively brief here. But again, I'd obviously be happy to work through some examples with you guys. Speaking of which, one of the other things I kind of want to do is, I obviously want to get you guys access to like content of me doing things as much as possible, but I also don't just want to make infinitely long videos that everybody feels obligated to watch, or you have to watch it just because you needed 5 minutes of it, stuff like that. So I've already had some pretty good interactions with people coming to office hours and asking me some pretty good questions, and hopefully you guys have seen that the kind of the digital document that I ended up making by explaining those problems to people. I'm just posting that stuff in Canvas. So another thing I'm going to be trying to do in a sense to sort of temper the length potentially of some of these videos here is to try and be minimal here, but so that when you guys then come to me with questions being like, well, I still don't get this from this section, we can walk through in office hours and I can post, either a video or a digital document there of the stuff that I've written. And that might be an easier way for us to sort of part out the things that we're interested in looking at rather than me just making, hour and a half long videos that I understand are sometimes difficult to kind of scan through for the stuff that you're looking for. So my goal is to kind of try and keep these slightly more minimalist. Not that I'm trying to give you less content, but I know that super long videos are sort of obnoxious, and it might be nicer if I, again, just come to office hours and ask me questions. And, you know, as you guys have learned, I mean, you've obviously taken a dozen math classes in your life if you're here. You know that if you have a question, then so do a dozen other people. And that means that you should ask because you're not dumb for having that question because a dozen other people also have it. And because a dozen other people also have that same question, it matters that I then share the answer that I've created with other people. So while, the pros list and the cons list for teaching online is not quite balanced, I think. One of the pros is that every interaction I get to have with one of you guys is actually something I can share with everybody. So keep asking me questions, and I'll keep on filling in the blanks for you guys by posting some of that homework help in Canvas. So let's go ahead and take a look at some cylindrical shells. So in all the cases that we've looked at here, we've needed to compute an area or a volume of an object, of the Riemann object, so that we could add up all of those areas or volumes to land at our total volume that we're accumulating here. I suppose I shouldn't really be distinguishing between area and volume here because even the Riemann sheets that we were thinking of in section 6.1 had that thickness of dx also. So really, I guess these are all like areas that we have been accumulating. Today is going to feel much more like a volume because it's not possible to describe the area in 2 dimensions here because we've got a hollow cylinder, a cylindrical shell. And by the way, sometimes cylindrical shell to me gives me a weird idea of what we're looking at in my head. For some reason, the phrasing a hollow cylinder is kind of like helping me think of what we have here. In any event, as you might be able to imagine, as I hope you guys sort of do, if you just go Google cylindrical shell and click on images, then it gives you about 1 billion images that various math professors have created to describe these things. You can even find exactly the images from our textbook in there and stuff. This is just one of the many, many images that I saw, and I snagged it because it's not that crazy. All I want us to realize is that what we're going to be doing is taking an infinite number of these shells stacked together, contained within one another, somewhat similar to our discs and washers. Discs and washers, I had a disc that was flat and we accumulated them vertically. These shells we are going to accumulate, in a sense, radially. rather than vertically or horizontally. So I think one of our big distinctions to make here is exactly that. Rather than accumulating Riemann objects vertically or horizontally, since our object is a shell and we're going to accumulate layers of the shell, we're really accumulating them radially, not horizontally or vertically. So what we need is we need to be able to understand what is the volume of just this shell right here. And the good thing about computing this volume is that it's really easy to do if you think about cutting it. So the thing that you should think about right now is like, how could you flatten a can? And so let me start my drawings here. If I were to take like a soup can, then what I could do is I could cut it vertically up the sides after having, opened the can. So imagine that I cut the can and cut the can. Then what you should be picturing is that I should be able to flatten this out into the bottom circle, the cut wide open part here, and then the top half of the can. So for a moment, just for your own sake of visualization, you should understand that this is a 3D can. And this is sort of an opened up can here, right? Here's the bottom of the can, the top of the can, and here's the sides of the can. But since I've snipped it vertically here and unrolled it, what I really landed with was just a rectangle, right? This is exactly the idea of what we're doing with the shell here, except the good news for you is that you don't have any tops or bottoms to work with, right? This is just an open top and an open bottom here. So the point is, I think that this is a relatively natural thing for us to think about right here. So if we imagine doing the exact same thing, taking our cylindrical shell and cutting it down a seam, that we could then open that thing up right there. And all it's going to do is form a rectangle. Now, one tiny technicality that I'd like to state is this. If this is truly a cylindrical shell, a 3D object, right? If this is a 3D object, then it's not really a Riemann object, right? And the Riemann objects, we're adding up 2D objects to get a 3D object. A Riemann object here would be the infinitely thin shell. The shell that you're looking at, I'm looking at it. It's not infinitely thin. So I just want to state geometrically, so we're all on the same page here. You should see that this has an inner radius and an outer radius. So technically, if we were to try and unwrap that shell, it would look a little bit more like this, right? And if you can see this, slightly more trapezoidal. Is that my word? Rhombus, trapezoid? The point is not square right there, because what you should see is that there's a larger radius on the outside than on the inside for when we cut that thing open. Wait a minute. No, I made my distinction in the wrong place right there. That's wrong. Where we should be thinking of this is going to be the same, this leading rectangle out here. But if I went to go draw like the 3D version of it, it's going to be more like it's going to be narrower in the back. That's what it's going to look like. Right, that would be my rectangle right there. And the important part is that that wasn't a vertical line right there. But the good news for us is that we are taking calculus, and taking calculus means that we're always talking about objects being infinitely thin. Therefore, that distinction between the inner circumference and the outer circumference will go to 0 as we turn this from a delta x object into a dx object, right? The Riemann object relative to the three-dimensional object that we're accruing here. So it looks like to find the area, or I should say the volume, the delta x volume, or the dx area of this cylindrical shell. The good news is we only need to understand the volume of a box, a prism right here. And that's way easy for us to handle right here. So there's some not very readable parts down there. Don't worry about it. I'm going to write it on the next page. All we need to have in our heads is that we have a cylindrical shell. We're considering the shell to have height. That's along the dashed line right here. And we know that this width of the rectangle is going to be exactly the circumference of the shell. And so you can see there's a little 2 pi r right there for that circumference. So let's go ahead and take a look at how we actually compute the volume of one shell, right? And again, this has been our really important thing in the last sections, is to say, tell me everything you can tell me about the individual Riemann object, then perform integration on the Riemann object to accumulate a bunch of them to get the next higher dimensional object. So in this case, we want to come up with the volume of the one shell. And when I say volume, I sort of kind of mean area. You should notice I left this as delta R, so technically it's a volume. If that's dr, then it's an infinitely thin. It's like taking a piece of paper and rolling it around, right, is all we're doing right there. So what we're going to get here is that the three dimensions of this prism right here, the long one is the circumference, the tall one here is the height, and then we've got the thickness that's associated with it. But because this is calculus class, the thickness will go to 0. That's our delta x going to dx right there. So the three parts of this volume is just length times width times height for our cylinder here that's been cut open. Our circumference formula is 2 pi r. That's the circumference of a circle. But what's r, by the way? We're going to need to talk about that. Our height, we've just labeled it as just h. The good news for you is that you know that the height of a graph is just its output value, its y value, f of x, right? And finally, we have the thickness that's associated with this. In my diagram up there, since this technically is a 3D object, this isn't quite a Riemann object yet, we have to make it infinitely thin. This technically does actually have a little bit of thickness, and so we call that the change in radius right there, delta r. So let's talk about a couple of these. In this description right here, r is the distance from the axis of rotation. Oh, sorry, that's okay. I confused myself with some bad grammar right here. R is the distance from the axis of rotation. So in the above image, it looks like this shell is oriented vertically, but hopefully, obviously, you guys are okay with the fact that we might have some shells that are horizontally oriented here. In this diagram, it looks like this radius distance is being measured through a vertical axis. So this vertical axis is going here, and our radius then, it seems like, would be an x measurement. It's a left-right measurement. It's the distance from the axis of rotation, the center of the cylindrical shell, to its edge. So in this diagram up here, we're going to have that r is the same thing as just our x coordinate. But again, you should keep your mind open to the fact that in other cases, your radius is going to be a y component right there if we accumulate shells in a horizontal direction there. In this case, h is the height, and it's always the height that is measured parallel to the axis of rotation. So what I mean by that is the axis of rotation is this vertical line that goes through the center. That is the same orientation with which we measure the height. So the height is measured parallel to the axis of rotation right there. The height is this directions of measurement. The height is always a measurement parallel to the axis of rotation. Whichever your rotation axis is, the height is measured parallel to that. Finally, the thickness is defined by us being in calculus class, right? That's going to be our change in radius, or since we've decided that in this image, r and x are the same, it should be the case that dr and dx are also the same as each other right there. So we can go ahead and use this to come up with a different form of integral expression here. What this says is go ahead and take the circumference times the height times the thickness. That's one infinitely thin shell. Integration says add up all of those infinitely thin shells, and we can do that from, as you can see, this is a dx integral, so we'll just add up all of the areas of all of those infinitely thin shells and along the radii that we want to experience them. So notice here, again, it's good to think about things like radii in this, but what we don't want to do is be in terms of r. So you should be thinking in terms of radii, but it should be the case that as long as our cylindrical shells are always oriented according to either the x-axis or the y-axis, or parallel to the x-axis or y-axis, that your radius should always be either a x measurement or a y measurement in these cases right here. So this is from an inner radius to an outer radius. In our diagram, our radii are oriented in the x direction here rather than the y direction, and therefore these are the a and b values are radii here. So what a reasonable person would do, what a smart person would do in this circumstance is say, whatever, man, we've already covered 2 sections of coming up with volumes. Are you serious? Why are we doing a 3rd section of coming up with volumes here? I'm pretty sure I can accumulate some areas and get some volumes here. So the book does, again, the thing that I like. Again, this isn't my favorite textbook on earth, but they do such a good job of saying, here's why other techniques don't work, and doing things like, here's a problem you've done in the past. Let's do it again and verify that we're going to get the same results, stuff like that. So I do like that they do that. So let's look and see what the book gives us as our, why do we care about this method at all? This is my not only Tony example one, but book example one here. And so in this case, let's go ahead and look to find the volume of the solid that is obtained by rotating about the y-axis, the region described that you can see there, and the line y equals 0. So this is essentially saying take this little mound and rotate it around so that we get the three-dimensional shape that's associated with that mound. You should notice that this mound has a height of 0 at the bottom, so it comes down to being 0 height at the center of the 3D object. You should see that the height of the 3D object is not completely clear. We could easily do some calculus though, take the derivative, set it equal to 0, and solve, and we would get the location right here. And by doing some super quick factoring, honestly, hopefully you guys could even just do this in your head, you're able to tell me that 2 is the location of our other x-intercept over here. So what I want to do first, since this is way more about the comparison than the actual answer to this problem, is, well, again, what a good smart person would do would be to be very skeptical. You should say, I don't believe you that I need a third method to do the same task. That's what a smart person would say, because it doesn't seem obvious why we necessarily need this here, right? So our issue here is let's draw the picture. Let's try and do this with the disc and washer method. If I'm using the disc washer method here, then what I'm picturing for myself is that these will be washers, and here is my representative Riemann object right here. This is the object that is going to be rotated around to form the washer, right? So what I need is my little r and my big R, right? Or my x, and maybe I'll call it x sub lowercase r and x sub capital R, right? I need my small radius and my big radius of the washer that we're trying to compute here. So here's the issue. What I need, I can kind of set up all my parts here. I know that what this integral looks like. I know that my washers are going to be accumulated. I know that I'm going to accumulate washers vertically. So I can tell that this is going to be a 0 down here up to some, wait, am I not getting myself backwards here? Yes. Okay, all right. I talked myself out of that for some reason. I hope that you just watched my moment of panic confusion right there and saw that we're the same person. Okay, good. So what I'm thinking to myself here is I am accumulating washers vertically. There's a whole stack of washers that are sitting on top of each other. So I know that I'm looking at a dy integral. I know that my y value is going to go from 0 up to mystery, right? But we can find it. Maybe I'll just draw that arrow right there, right? That's the heights right there. Some y value for our upper bound. I could find it. I don't care to find it. I could, but just notice it would take us a little work. I hope that you're all as lazy as me. We're kind of trying to avoid doing that. So what I need here is I need some expressions in terms of y, right? I need some stuff in terms of y here. Like this has to be some pi r squared times pi r squared, but here's my real issue. This is like pi x sub r squared, x sub r, capital R, minus pi x sub lowercase r squared right there. But here's really my big issue. Can you solve this for x? Because I cannot. This is a cubic. When I say I cannot, what I mean is I am too lazy to, because I don't want to go to Wikipedia and look up the cubic formula. Technically, this equation could be solved for x in terms of y. Technically, if we were able to do that, we could go ahead and throw the upper and lower bounds in here. We would end up getting like a one chunk and then another chunk right there. There'd be two different expressions right there, some positive or negative. We would use those for these two different branches right here. But like, I don't know how to do that. I don't know how to solve this thing for x, right? I can't solve for x. And therefore, I don't know how to continue setting this guy up, right? So like, I think I could technically draw the picture and write the integral that represents this for the disc and washer method. And by the way, when we go to take our first test, I'm probably going to do something like say to you, find the volume of this solid using any method. And I'm going to give you one that's just not going to work out in other methods exactly like we're going to look at here. And then I'll say, as like a part B, I'll say something like, draw the picture and set up the integral that would be associated with the volume using a different method, but that you won't be able to do, right? So that this given on the screen right here would essentially just be like your final answer to a part B. It's like, this would be the disk and washer method integral. I just can't do it because I can't solve for x. And that would be kind of an alternate format for this guy right here. So again, our dilemma here is that we need to be able to algebraically manipulate our function of interest, and not all functions of interest are going to be algebraically manipulable. Manipulable, is that my word? Manipulatable. And so we're just stuck here just based on the fact that I can't solve cubics, right? It's not a calculus issue that we've run up to. We've run up against an algebra issue, not a calculus issue right here. And as promised, that never stops being the hard stuff. When you guys all come take differential equations with me next semester, I'm gonna really teach you some algebra next semester. I think that you all think that you're good at algebra, but we'll see. So let's do this a different way. What I'm now picturing for myself alternatively is that if I'm going to do the cylindrical shell method here instead, then I am picturing this being my Riemann stick right here. Here is my Riemann stick. That's the Riemann stick that I'm rotating around once to produce one shell. Then we'll do that for all of the possible shells. Okay, so again, picture rotating this upper Riemann stick here about this axis, and you should see that you're going to get a washer shape. Rotate this around the y-axis, and what you should see is that, and actually, let's just stop and say this real quick, a washer is a cylinder. But we are picturing in the washer scenario that the infinitely small part is the thickness, the height. The height is what's infinitely thin for the washer, but there is a gap between the two radii. In the cylindrical shell, the height is actually there. We do have a finite amount of height. It's the thickness that's the infinitely small part. Maybe I can sort of like draw that idea right here. Here, so one good distinction for us to make here is that what's the component of our object that's infinitely thin? And again, stop and convince yourself that a washer is a cylindrical shell. The only difference that we're making in a calculus setting is we're saying, of the three dimensions, which one do you want to make the infinitely thin dimension? In the washer scenario, we smashed it flat down onto the table. In the cylinder method, it's not smashed into the table, but the thickness of the walls, that's what we smash down to be infinitely thin. You can see in the washer, the walls are not infinitely thin. Capital R minus lowercase r is a number that you can compute, right? It's knowable right there, right? So realize that we're actually coming up with just an alternate version of the same object. This is still length times width times height. We're just picking a different dimension to be the infinitely thin dimension when we say that this is a cylindrical shell rather than a washer. So the good news is that this is going to work out pretty dang nice for us right here. All right, so again, I'm thinking of my integral right here. So I know that my axis of rotation is the y-axis. So I'm going to scroll up here because I want to revisit some of the statements that I made up here. In these cases right here, one thing I know is that we're always looking to set up our integral as a circumference times height times thickness. In this case, my circumference is going to be 2 pi r. And in this case, my circumference here is my r is equal to x, right? The radius to get to the edge of my cylindrical shell is r. And in this case, we're measuring that in the x direction. So you should really think 2 pi r In our case, because of the way that we have oriented this image, the radius is equivalent to the x value. The height, well, that's super nice. The height of a function is always the y value, right? The height is y, that's f of x. Well, I've got that up here. I scrolled up a little far, but that's our 2x squared minus x cubed. That is y, 2x squared minus x cubed right there. Finally, how thick is our cylindrical shell? It's infinitely thin. And we are accumulating that infinite thickness. It's being measured in the x direction right there. Since I know that I am computing a dx integral, all I got to do is stop and think to myself, what are all of the x values for which I should be computing one of these cylindrical shells? And I'm going to go back to this over here and say, this is the same question as me asking, what are all of the radii of the shells that we need to experience? Well, I need to experience the shell at biggest that goes all the way out to 2. And notice, by the way, technically speaking, the cylindrical shell out here at 2 is going to have 0 height. But you know, we're doing our infinite accumulation here, right? So I want a radius of 2 all the way down to a radius of 0, or all the radii that we're going to experience, all the x values that we're going to experience. So 0 to 2. So hopefully you should see that we're essentially done here. Now we just got to do some integration right here. So let's go ahead and do that integration and see that, you know, at the end of the day, this is just an integral of a polynomial. For the 100th time already, only in day 2 of week 3, I'm going to say to you, setting up integrals is usually harder than actually evaluating integrals, because every integral is pretty much usually hard to actually evaluate. The setup is the important conceptual part here. So what do we got? First things first, bring the 2 pi out front. Second thing, I'm going to multiply x into each of these guys. So 2x cubed minus x to the 4th dx. Now we're in much simpler shape. Remember, you should always be doing as much algebra as you can before you do integration. Integrate the easiest things you can ever integrate, always. 2 pi, and doing my integration here. So currently the power is 3. The integral should increase the power to 4. I need to introduce a coefficient of 1/4 to cancel that out. So I'm going to get a 2 over 4 x to the 4. You should notice if we take the derivative of this, the 4 will come down and cancel with the 4 in the denominator, leaving us with 2x cubed. 2x cubed is right there. Minus, the power of 4 is going to raise by 1 to be the power of 5. But I need a 1 over 5 to compensate for the 5 that would pop down from the derivative. The derivative of 1/5 x to the 5th is x to the 4th. And we're going to evaluate this guy from x equals 0 to x equals 2. Oh my gosh, we just get given gifts all the time here. Oh man, this is just all day long. Polynomials evaluated at 0. This is just the best thing ever right here. So evaluating 2 pi, that's a 1/2 there, 2 to the 4th, minus 1/5, 2 to the 5th. And we can do a little evaluation. 2 pi, that's really just 2 cubes, that's 8. Minus 32 fifths. Ugh. I guess 8 is 40 fifths. And so 40 minus 32 will give me 8 fifths. And so 16 pi fifths. And we've managed to compute our volume there associated with that guy. All right. So again, the doing of the integration, I hopefully feel that, hopefully the stuff that's just on the screen right now is easy for us right now. The hard part's the setups here. We just want to be able to visualize the objects that we're creating. So I'm going to scroll back up real quick here and shake my fist at you guys some more, and then we'll move on and look at a second example here. Again, washers are cylinders, and cylinders are washers. The only difference is which dimension is the infinitely thin dimension. A washer has been smashed down flat onto the table. It is infinitely thin in this dimension. The cylinder is infinitely thin in this pinchy direction right here, right? It's got infinitely thin walls. The wall of the washer is not infinitely thin. It's capital R minus little r thick. That's the thickness of the wall. Here, the thickness of the wall is dr. It's infinitely thin radius right there. It's capital R minus r. But as we accumulate infinitely many washers that become thinner and thinner and thinner, capital R minus little r is going to drop down to zero out there. Right? We should remember that when we're accumulating these areas, I think this statement is probably the most useful thing I've said or written so far this entire time. You should be thinking about this in terms of geometry that you know, then replacing geometry ideas with the actual components that we actually have built right here. Circumference is 2 pi r. Your only job is really to decide what direction we're measuring these things in. What's r really going to be? You literally might want to write actually 2 pi r in your expression. Like, I don't think it's a terrible thing for us to have actually, like, to write this as like 2 pi r times y times dx. Like, I think that's a totally fine way to get started right there. You then need to decide for yourself that r is x, and you need to decide for yourself that y is 2x squared minus x cubed. But this is generic circumference, generic height, generic thickness right there. We just have to, in a sense, substitute in the appropriate values relative to the orientation of the shells that we're constructing. So, pretty visual section here. I would certainly encourage you to look at all like the book just has pictures that are so good that I just cannot draw. And I feel like the next like $1 billion idea is like, who's going to make me a 3D Desmos? And by the way, we will look at some CalcPlot 3D things this semester. They just are not very helpful for our surfaces of revolution. But there is actually sort of a Desmos for adults that exists. It's CalcPlot 3D. And if you're taking Calc 3, especially I think Jackson's teaching it again next semester, he's going to have it open literally every single day of the entire semester because it's such a three-dimensional class. So picturing this stuff is important. So I would encourage you, I literally can't draw the pictures that are good that go with this. So it really matters that you see the well-organized pictures in the book. I think that they draw every single diagram. That's what I really need to see in the book for orienting these cylindrical shells here. So make sure that you kind of, have those images in your mind. I think this is a very visual and spatial section here. But alternatively, remember, this can easily be thought of as a geometric section here as well. Circumference times height times thickness is just how you compute the volume of a shell. And so we can literally just write it like that and sub in our 3 parts here. Okay. So there's our first cylindrical shell method. And again, I really like that the book immediately gives you an example of something that wouldn't have worked in the previous 2 sections because of our inability to get there algebraically. So again, right before I go on to my other one right now, which we will do 2 ways again, I just want to say, like, one of your goals in working through these 3 sections is hopefully that you're developing a sense of intuition for which technique might be the most appropriate in which case. It's not always going to be like, I'm certainly not going to say to you, use this technique to find this volume. I'm just going to say, find this volume. So on the one hand, it's totally the case that like you might be like, discs and washers are easier for me than cylindrical shell. I'm going to set it up. You get to this point and you're like, crap, I literally don't think I can actually finish this from right here. That's your good indicator to go and attempt a second technique. And so realize that guess and check. I kind of laugh because I think that in life, when you're like very uneducated, all you know to do is guess and check. Then you learn a little bit in school and college, and you're like, no, I can actually compute some values of interest. And then once you get to enough math, you realize, man, most of the values of interest to me are really difficult to compute. And it's actually maybe better for me if I do lots of guesses to kind of head myself in the right direction. I kind of think that guess and check is sort of like one of the lowest forms, but also one of the highest forms of problem solving, depending on how academically you approach your guessing and checking here. So realize that you might just get stumped, and that's why we got 3 different techniques here, is to say, okay, looks like disc washer didn't work out. Let's try it with shells instead, see how it goes for us. So let's do another example here, and in this example we'll do both methods. We're going to do cylindrical shells, and we're going to do disc washer as well. This example is number 8 from the homework section out there. In general, I'm trying to grab, I want to grab homework problems from the book, because I want you guys to know that like that very much matches up with what you should expect from the My Open Math homework. I'm going to continue to try and grab the evens out here so that if you guys want to give yourself practice with the odds, I'm not necessarily stealing the good problems from you right here. So this is my hope for this guy right here. In both cases, draw a diagram to explain your method. That's really important here for these guys. So let's continue to draw these diagrams here. So I think we should do this slicing first because that's the one that we've been doing first. So when they say by slicing, I'm going to say disc washer method here. So in this case here, fortunately, these are two simple functions that we're very, very comfortable with. Y equals root x, y equals x squared. So the picture is the same for both of these. The Riemann object is different, but the graph is the same. So there's square root of x. There's x squared. We know exactly where those two intersect. I hope nobody's confused about this one still. One squared is one, square root of one is one. We are interested in finding the volume that is obtained by rotating this area about the y-axis. Okay. So if I am thinking about this as a disc or a washer, I am picturing a Riemann stick here. I am picturing that I want to come up with it appears that this disk has an inner radius of an x value and an outer radius of an x value right there. I need to come up with little r and with big R right there. This is our root x function. Ooh, by the way, sorry, I'm going to go back and just even rewrite that. I can't just write an expression. It matters that I have an equation for these guys here. So y equals x squared and y equals square root of x are those two functions right there. So it looks to me like if I'm going to do my disk or washer method here, I'm going to set up an integral for myself here. I know that we're looking at some version of pi r squared minus pi r squared. And it looks like if I'm doing this disk or washer method, I am accumulating a vertical stack of these washers. A vertical stack of washers. So I am going to do this as a dy since I'm accumulating a vertical stack of washers. Now that I've decided that my integral is with respect to y, I know that I can pick out the y bounds that are associated with my graph here. This one's a gimme since the x bounds are the same as the y bounds, but it's the case that I'm picking y equals 0 to y equals 1 right there because I am imagining a vertical stack of washers. All we got to do is find r in terms of y here. So the important thing is that, let me maybe say this as r, little r. I'm going to call that x sub r. And capital R, I'm going to call that x sub capital R. We want to recognize that these x's are coming individually from these two functions over here. So notice my inner radius, the smaller of the two x values, the smaller of the two radii, lowercase r, is based on the y equals root x function. And so in that case, my little r stuff, that's talking this x and this x are the same. So maybe this says to me, I want to think about y equals root x or x equals y squared. And so in this case, then I would say r is x sub r is y squared. Right? And that's because I flipped this equation basically. Instead of y equals square root of x, it's x equals y squared. That's my lower radius. My larger radius, my capital R, is also an x value. And it's the x value that's corresponding with the desired y value from this equation here. So it's here going to be the case that y equals x squared, x equals plus or minus root y. In this case, it looks like we just have the positives. We're only in the first quadrant over there. So I'm just going to write that as root y for measuring our height. And that says to me capital R is what we're calling the outer radius as measured in the x direction, and that is root y. So I now have the pieces that I need to do this with the disk washer method here. So it looks like my integral is 0 to 1. Those are y values, 0 and 1. I've got, and I'm going to do my, well, okay, never mind. So, by the way, if you guys remember last lecture, I did like a dumb little factoring thing with my square. I did the exact same thing when preparing my notes for today, and I was like getting the wrong answer. I'm like, why is my answer wrong? And it's because I'm doing stupid squaring things again here. So don't make all the same dumb mistakes I'm making. So here, this should be root y squared. And again, how did I know, by the way, that I need to convert these into y statements instead of x statements? That's because this was dy. I needed my radii term, little r and big R, to actually be expressions of y, not expressions of x. That would be the wrong variable to integrate over with the dy sitting here on the end. This is going to be minus pi times y squared squared. That's the squaring that I forgot to do. Basically, since that y was already squared, I was like, yeah, pi r squared, got it. And then I forgot my outer squarings right here, and I was getting the wrong answer earlier. So again, I'm going to say it for the bajillionth time, and I'm going to say it a bajillion more times. The hard part's setting up the integral. This is the tough stuff to get to right here. Doing this integral is going to be super easy because it's just polynomials. So let's go ahead and compute our integral here, evaluate this guy. What do we got? I'm going to pull the pi out front first. Always do your algebra first. It looks like this is just going to be y minus y to the fourth dy. Evaluating my integral. Y to the 1, we're going to add 1 to the power, so it's now y to the 2. Since our new power is 2, I need to introduce a coefficient of 1/2 to cancel the coefficient we would introduce with the derivative. In our second term, y to the 4th is going to become a y to the 5th. But since our power is now 5, I need to introduce a 1/5 so that when we take the derivative, we get back to y to the 4th. This is going to be evaluated from y equals 0 to y equals 1. And I know that all of you are writing things like y equals here and x equals here as appropriate and never just writing a single individual number that you don't know what variable it belongs to, because if you do that, then you are going to have a bad time in Calc 3 next semester when there's a ton of variables floating around. I can't make the whites of my eyes any bigger or else they're going to dry out. Keep writing those little x's and y's in there. So here we are. Let's continue evaluating. Oh my gosh, we've been given another whole gift right here. We're evaluating a polynomial at 0 and even better at 1 up there. So this is really just 1/2 minus 1/5. And what's that going to give us right there? That's pi times 5/10 minus 2/10. And I'm going to be getting here 3 pi tenths. Okay. Just for our people that are needing that little bit of help there still. Good. Evaluating the antiderivative at 1 gave us 1/2 minus 1/5. Evaluating the antiderivative at 0 just gave us 0, so I just didn't even write it. All right, so it looks like our answer is 3 pi tenths. And again, we could have done this problem already. This was, I just did 6.2 stuff right there is all that just happened. What we now want to do is stop and say, would we get the same thing if we attempted to do cylindrical shells here instead? So rather than picturing a vertical stack of washers, we are now picturing cylindrical shells that are going to increase in radii from the center, and they're going to sort of grow outwards until they hit the edge. And accumulating all of the appropriate areas of those shells is what's going to get us our total volume. You should notice that in the previous case here, all of these cylindrical shells, they all sort of sat on the ground and they all had different heights, but their bases were all the exact same. So notice in this case right here, it's actually what I probably should have written this as is this expression minus 0. I didn't because minus 0 doesn't do anything, but you should notice that the height of a stick is not just its y value on top, it's the y value on top minus the y value on bottom. Here the y value on bottom was 0, so just the y value on top was the height. Here, the height of our upcoming stick is going to change because notice it's going to have a bottom that's based on a function, not based on the x-axis. So the only real difference for our next part is that rather than just throwing in one function here, we actually sort of have two functions to define. And we did here, actually. If I want to really be serious about this, there were two functions. We were given two bounding functions, upper bound, lower bound. I just didn't write minus 0, but technically it's there, and it's probably good to kind of mentally keep track of those things. So let's do it. Okay, so I want to draw the same picture. Where are we at here? I want to draw that same picture. But this time, we're going to get a Riemann stick that's got a little different shape. So, same idea, same stuff. Y equals x squared. Y equals square root of x. A little crappier picture here. That's okay. Important to label these. And even more than that, as you saw me change it last time, don't just label these as root x and as x squared. The equation helps because whenever we have to do this back and forth solving for other variables, you don't want to be confused about which x or which y you are referring to. So in this case, we are going to now accumulate a bunch of cylindrical shells. As promised, the infinitely thin part is different. In our previous example, the thing that was infinitely thin was the height. And so we had dy. That's our infinitely thin height. In this case over here, the thing that's infinitely thin is the x parts that are right here. And we are going to accumulate them from 0 to 1 across the x values here. So it's really technically the same shape. It's just your same geometric shape. It's just with the different dimension being the infinitely thin part here. So I know with my method of cylindrical shells, I know that I want to think about the circumference times the height times the thickness. And man, you should probably like literally write that as your first integral for every single thing for the shell method, because like this is my organizing of my information right here. This is how I know what I'm doing, is by writing that. I think there's probably some math people that would get semi mad about there being no variables and no bounds of integration, but that's not what I need for me to understand this. Concept wise, this is great. So let's fill in all those gaps now. The circumference is always 2 pi, and I'm just going to write it as r. What are our heights here? Well, maybe we should do something like this. Let's call this a y1 and a y2 so that we don't get any confusion here. It looks like in this case y2 is always on top, and it looks like y1 is always on bottom. I sort of accidentally picked them that way, but I always like doing thing upper minus lower, 2 minus 1, stuff like that. So here I'm going to say y2 minus y1. How thick is this stick? Well, it's infinitely thin in the x direction, delta x, or in our integral land, dx. Since I now know that I'm going to integrate dx, that tells me a couple things. One thing it tells me is I can now go ahead and pick out an x boundary for my bounds of integration. It looks like since I'm in dx, we need to span the x values from 0 to 1. The other thing I know I need to go work out is what's r, what's y2, what's y1. I need all three of these things actually to be in terms of x because I have a dx integral. It looks like, in this case, 2 times pi times, and I'm noticing here our radius from our axis of rotation, which I probably should indicate here, our radius is always the distance from the axis of rotation to our representative stick. In this case, that distance from the axis of rotation to the stick is exactly the x value that we're currently sitting at. So 2 pi x times y2 in terms of x is root x minus just x, x squared up there, dx. Let me make sure I'm not going crazy right now. Okay, good. Double checking, because like I said, I made the same dumb mistakes when I was preparing my notes for today. So again, we went from most general to the basics in terms of any variable that we wanted. Now to actually do the computation, we need the variable consistency. So we forced all of our r's and y1s and y2s to be their respective appropriate variables here. And I should say right here, r equals x right there. The radius is the x value. So now we can go ahead and evaluate this guy. We know what answer we're expecting. We're looking for that 3 pi tenths from last time. And so let's see if we get this when we evaluate. I'm looking at a 2 pi, because I always want to do my algebra first, factoring some stuff out. 0 to 1, those are x values. I can see here I'm going to be helped by multiplying x through this quantity. Also, square roots are dumb in integrands. That's an x to the 1/2. So as I distribute this x across these guys, I'm going to get an x to the 3/2, right? That's x times square root of x is x to the 3/2 minus an x cubed dx. And let's go ahead and do the integration. 3/2, if I add 1 to the power, I'm going to get x to the 5/2. When I introduce the power of 5/2, I need a coefficient of 2/5 out front to even everything out. Now if I take the derivative, I get back to x to the 3/2. When I have x cubed, the power of 3 becomes a power of 4. Since there is a power of 4, I need to introduce a coefficient of 1/4 so that the derivative of 1/4 x to the 4th is x cubed. And we're going to evaluate this from x equals 0 to x equals 1. And let's go ahead and evaluate. 2 pi times, and man, all the time, oh, it's so great. We've just been handed the simplest possible evaluations of all time. Evaluating a polynomial from 0 to 1, it's never, ever going to get better than that. Unless you're doing integrating trig functions from 0 to pi, right? That's about the only other comparable thing here. So all I'm going to get is just 2/5 minus 1/4, and that's it, right? Minus the f of 0, but that's just 0 right there. Oh, integral from 0 to 0. What a good question. So if we're integrating, sorry, sidebar right here. Actually, sorry, I'm going to wrap this up and then I'm going to come back and answer that because that's a really important question that you're asking right there. And then I'll reference a document that's in Canvas and then we'll wrap it up and call it a day here. So just to wrap up this evaluation right here, this is 2 pi times, I'm thinking our common denominator is 20ths. So I'm going to multiply this by 4 and get 8 20ths. I'm going to multiply this by 5 and get minus 5 20ths. And that's going to give me 2 pi times 3 20ths. And 2 and 20 are going to cancel with a 10 and give me 3 pi tenths. And that's good, because that's exactly what we just got with our previous example over there, right? Or with our previous method for the same example, and that's what's important. So it's definitely the case that a couple of these problems are all about like, hey, do this both ways. And there is definitely value in doing these both ways. And there's a 100% chance that on our first test, I'm either going to say, do this problem using 2 different techniques, or I'm going to say, do this problem with one technique, then set up an integral for another technique that you can't do, but at least set up the integral for it, right? So there's a guarantee that we're going to do this sort of comparison of 2 techniques thing on the test, and that I won't say like use cylindrical shells. Like it's up to you to sort of decide that. And so, as I'm just sitting here ranting about awesome bounds of integration, we've got a little question in chat there. It's asking questions like, what happens when we get this stuff right here? And what you want to remember is that we are talking about, if we have some f of x function out here, this is really like saying now, how much area is underneath 1 point? Well, that's truly my 1 Riemann stick. And what we know is that 1 Riemann stick will never impact the overall sum because this is 1 infinitely thin sliver. This is like taking an infinite number of pages of a book and extracting 1. The book is still the same thickness. That's a kind of bad analogy because that's very technically not true, but that's sort of our analogy for these things. What I would like to relate this to is, if you guys saw in week 2, I posted a little blurb about thoughts on integration. And I think this is a great idea right here, that when we think about, area under f of x over the interval a to b, open interval, is equal to the area under f of x over a to b, because the only difference between these two is that this second integral, in a sense, has 2 more Riemann sticks. It does, but the area underneath the Riemann stick at a is 0, and the area underneath the Riemann stick at b is 0. So there's no actual additional area that's accumulated right there. So it takes more than 1 infinitely thin thing to get you some actual 2-dimensional area. So these integrals, if we have the same bounds of integration, it's always zero. And there are words that say the answer to this is there is no area underneath a point. You need to have an interval to accumulate some area that's beneath that right there. And so since I did just bring it up, I do just want to mention to you guys, if you didn't see it at the later part of last week, I wrote like a 2-page thing on, and this is this is me getting out there. This is my hippie math now. There's no math that happened in that document, thoughts on integration, but these are sort of just ways in which I think about how I envision Riemann objects being represented in my own life. And so if you guys want to read that and kind of write back to me a little bit about that, that is acceptable for your weekly writing associated with either week 2 or week 3, since those are kind of the 2 weeks that we're talking about integration and Riemann objects. So if you're looking for a weekly writing topic for either last week, which is due this Saturday, or this week, which is due next Saturday, you are welcome to kind of read the thing I wrote on the thoughts on integration that's posted in our week 2 module. I will also post it in our week 3 module, so it's in both places. You're welcome to read that and in a sense extend it. If you haven't read it yet, it's really just like 4 ways that I kind of envision integration in my life. And if you would like to, in a sense, add a 5th, talk to me about a way in which you maybe see a similar thing that I see, then that is an acceptable topic for your weekly writing rather than standard things for the weekly writings that are out there. So I think this is better. Like I said, I want to kind of keep these somewhat shorter. Every time I hit an hour and a half, I'm like, ugh. An hour and 12 minutes, plus that being 10 minutes of me being delayed at the beginning right here, I think is a little bit better. Again, I'm certainly happy to do more of these examples with you guys. Where we're at right now, if you see above my head right there, we're going to talk, the section is called work. We're talking work in the physics sense. It's not just saying this section is going to be a lot of work. This section, although it is going to be a lot of work, it's going to be a lot of geometry and careful diagramming, which is a significant part of most physics things here. If you guys have looked, I posted the by hand homework for the week, and I did give you a very good work problem, which is measuring the number of joules to perform a certain process. It is left very general, but it's also, I basically told you where you can sort of basically just look up the answer. So you should do that if you do need that help, right? And you should, you're going to need help for these, but I want you to use the help. That's an appropriate way to use that resource. So this week is going to be a little bit screwy here. I basically think my plan is to basically just cut Wednesday out of this week is essentially what's happening. Monday happened on Tuesday. Tuesday is happening on Wednesday. Wednesday just isn't happening. Thursday is happening on Thursday, and Friday is happening on Friday. So basically what that says to me is I am definitely happy to answer your guys' questions via email, or we could even, in a sense, kind of arrange a bit of Zoom time, but I'm going to do tomorrow another day of lecturing rather than the regularly scheduled morning and afternoon office hours that I have there. But that doesn't mean that I can't answer your questions. I'm still planning on doing all that. Thursday is not too late for me to be answering your questions, so I will be available. Oh wait, but Thursday we have. Okay, Thursday I technically only have 2 statistics office hours, so I'll say to you, yes, I'll send you guys a time that I'm down to meet, or if you just want to email me, let's just say I'm down to do Zoom stuff on Thursday, even though we don't technically have an office hour arranged. If you just want to talk about doing some stuff, hit me up and we'll make a Zoom meeting happen on Thursday. Otherwise, those are just the problems, the couple different versions of things I was looking at doing here today. Cylindrical shells is just another alternate version of things we've already done in 6.1 and 6.2. And so I'm hoping that you guys kind of see this for what it is, which is not some new big wild idea, but another just careful organization, careful accounting. And I'd like to just, I can't say it enough, setting up the integrals, that's where the magic happens. This is the whole meat of this problem, is basically these 3 integral statements right here. This is what helps me know that you know exactly what you're talking about in 6.3. This is what tells me that you know what you're talking about in chapter 5. Right? This screen is chapter 5. This screen is chapter 6. This is the big key concepts here, is being able to go from this statement to this statement to this statement based on a diagram and a description right here. So work on those things. You got I was a little behind this week because of my little trip out of town this weekend, but I've got the My Open Math homework is up. The by hand homework is up. I think I posted the weekly writing, but if I didn't, I'm going to kind of wrap up the rest of our Canvas stuff here for this week. And stay in contact with me. I'm going to go and answer some more My Open Math and email questions right now since I'm done with my representative tasks for the day. And I will see you guys. Thank you guys that were here in chat asking me some questions. We're going to talk 6.4 tomorrow on work. Might be, it depends on what kind of person you are. If you're a physics person, this is going to be easy and you're going to be good to go. If not, there's going to be some new concepts in here for you. And maybe my last thing to say for the day, since I'm talking about the sections of the chapter, is section 6.5 is definitely the easiest section of the whole chapter. So average value of a function, like literally, it's like 2 pages in the textbook. There's nothing. It's just averages. It's literally all that's happening in there. So that one will be easy. So I'll see you guys for work tomorrow. See you guys then.